Hello all, welcome to day 7 of sound and mechanical waves. Today we'll be talking about two concepts, all right? How waves interact with each other and this resulting third frequency called the beat frequency. I will need to talk about a bit of background first, so I'm going to talk about something that we covered yesterday. No, you do not need to copy this down, but this properly explains why resonance columns behave the way they do, all right? Because yesterday, this is all you saw. You saw that I just drew a curve that looks like this, another one that looks like that, and another one that pretty much looks like something ugly like that. Probably drew too many curves, but I hope that you get the idea. There you go. That's a better rendition of it. Okay, so I just drew you a static picture, and that's it. And that's the problem about textbook. They only show you a static image. And all the static image really tells you is that, yes, a node will be formed over here, and an antinode will happen on the opening. All right. And yeah, that's probably sufficient enough for a static image. That's the best you can do. But you got to remember that this picture changes as time goes by. All right. Waves are coming into the column. Waves are bouncing off and returning back. And what you're really seeing in these pictures over here is the superposition of the transmitted wave and the reflected wave. So you're seeing the sum of the results. You're not seeing everything as it's happening real time. So let me just show you what's happening real time. And you have to mentally think about, how to add it together to get these results over here. This is what I mean. Let's say that you have a wave entering in, okay? And these are all the same wavelengths, as you can see, right? They all share the same exact wavelength. The only thing I'm altering is the length of the tube. And you can see by the length of the tube, it will either interfere in such a way that you have constructive interference at the opening, so it'll get very loud, or it may result in destructive interference where the sound effectively cancels out. So yeah, it is possible to take a tube and cut it to a certain length that it will cancel out sounds, all right? So you can naturally do sound cancellation with physical objects. You don't have to have sound canceling headphones to do that. You could do it naturally with physical tubes, okay, as long as you know the math behind it. So in all these examples, as I said, we're going to stick to the same wavelength, but we're changing the tube, and let's see the outcome of it all. I'll start off with lambda over 4. Okay. So with lambda over 4, as it's entering in, remember that you're going to have a complete inversion. So if it enters in as a crest and hits the wall, it's going to return as a trough. If it enters in as a trough, it's going to reflect as a crest. So the red wave represents the incident wave to that boundary, and the purple wave is the immediate reflection as time goes by. Okay, so I hope you can see that right now. Okay, so a trough results in a crest, and a crest immediately creates a trough. And this is happening in real time as time goes by. Okay. Now the next thing we're going to do is we're going to analyze what the outcome is on the far end. Okay. So let me just start the animation one more time, just so you can quickly see it. As it's transmitting in, you'll see that we have a trough right now in the incident wave. Hey, look at the reflected wave. It is also a trough. So trough plus a trough creates a super trough. All right. Also, at another moment in time, we're just going to wait for it. Okay, we're going to look at this wave point over here. The moment it meets the opening, you'll see that it's a crest. But the return wave is also a crest as well. And a crest with a crest creates a super crest. So we got our super crests and we got our super troughs happening at the exit. And this is all happening real time. All right. But as a textbook, unfortunately, textbooks cannot animate this out. As a textbook, when you see a picture like the static image over here, you effectively have this negative value plus this positive value, and that adds up to an answer of 0. You then have this positive value plus this mid value, and it gives you that mid value. And then all you end up getting at the end is that subtraction of that. You end up getting just this. So you end up getting that part of the curve. And just to finish it off so you can see the entire curve, they end up dotting the other side. So that's the difference between what a textbook shows versus a real-life animation. I think I have some questions already. Super trough is when you have a trough added up with another trough. Okay, so bottom side plus the bottom gives you double strong bottom. Top plus top gives you double strong top. And that's how these tubes are able to amplify sound, because you're meeting, well, actually there's two impacts of it. First off, when the timing, because of a quarter wavelength, when it enters in and when it returns, because the return and the incident match up to the same, that doubles it. On top of that, remember, when you're going from medium to a vacuum space, remember that it does that little whip thing? It doubles it as well. So that's all the amplification that happens. It's transmission, the reflection, the whipping of the reflection, and it amplifies it. And it doesn't just happen once. It keeps on going over and over again, because that whipped reflection will reflect back in, go back up, amplify again, go back in, amplify out again. And that's why these are known as resonance columns. They'll allow the sound to amplify and get very loud. Now, for a closed air column, I don't really have the equipment to demonstrate it for you. That's why I kind of stop with just that. But you've seen resonance happen with this cool thing. All right, it's literally what's happening over here. Sound is being transmitted. It creates the whip. That whip reflects back in, and it's just timed out perfectly because of the length of this, that every single time it jumps back and forth, it creates a super crest or a super trough here, making it crazy loud. And that's the science behind this. Okay, and you can repeat it again for the 3/4 wavelength. I'm not going to pause this right now, but just look at it real time. You can see that by time-wise, crests will double up and troughs will double up. And again, if you take a look on the right-hand side, you'll always have a crest with a trough because they'll cancel out, or a trough with a crest, they'll cancel out, or a rest with a rest, so it'll cancel out. And that's why every single time when you animate through the second one, you're always going to have something that looks kind of like this. Node there, a little lobe, and then another half wavelength, kind of like that. It's hard to draw as well. Okay, it's going to look, yeah, excuse my terrible drawing, but it's going to have some pattern that looks like that. There you go. That looks better. Yeah, you get that. Okay, so that's why 3/4 wavelength looks like that. Okay, 5/4 wavelength, I'm just going to animate it. All right, so if you look on the right-hand side, you'll notice that mathematically, they'll always end up to an answer of 0. That's why nodes are drawn in the static image in those 3 cases. And if you look at the extremes over here, you got there you go, just pause right there. You have a trough with a trough, which adds up to a super trough. They'll add up like that when you do the mathematical sum, or you get a crest with a crest. And that happens every single time at 1/4 wavelength, 3/4 wavelength, 5/4 wavelength, 7/4 wavelength, 9/4 wavelength, 11/4, 13/4, so on and so forth. You'll see that there's a mathematical pattern, and that is known as an arithmetic sequence. Right? It's a topic covered in grade 11. Okay, now what if you decide to use these lengths over here? And this isn't really mentioned in the textbook, but I do want to point it out. There are lengths that can cause sound to cancel out as well. All right, so no, we're not talking about any formulas here, even though you can generate one. I'm just telling you that that occurrence can also exist. You can have sound cancel out as long as you mathematically make the tube the right length. Okay, so coincidentally, if you set it up at lambda/2 for a closed air column, this is what's going to happen. Okay, look at what happens right at the opening right here. You end up having a trough interacting with a crest. They cancel out. Or you have a crest interacting with a trough. They'll cancel out. Okay, so here's the crazy thing. Between a 1/4 wavelength and a 3/4 wavelength, you'll have a moment of silence when you stretch it out. It's a demonstration that I can't show to you here because I don't have the equipment, but if you ever get to see a water column in the future, you'll notice that whenever they do them in demonstrations, maybe I'll make a video on it in the future when I get back to the school, I'll fill the water all the way up to the brim. I'll start draining the water, and at the 16-centimeter mark, it'll get very loud. Okay, the next time it'll get very loud, as we calculated early, is at 50 centimeters. So it'll be very loud here, then it'll get quieter and quieter and quieter, and interestingly enough, somewhere over here, it'll be so quiet that no one will hear. And that's because as the wave transmits downwards and it reflects back upwards, it's in the opposite phase as the wave that's coming in. So it's a positive wave plus a negative wave interacting with each other, a node is formed, it is canceled out. So it's really loud at 16 centimeters, really loud at 50 centimeters, and it does cancel out somewhere in between, and you can do the math for it if you're interested. I think it's somewhere in the 33 centimeter mark, somewhere around there, okay, if you do the math for it. Okay, so that's what I wanted to talk about. That resonance, it is a real-time animation, and you're looking at the real-time outcome. And in fact, that's something that I keep in mind with regards to what I'm going to talk about next. That's why I wanted to go with the backstory here. Okay, so this is the answer from yesterday. Let's talk about today's lesson about interference of waves. Okay, now we're talking about interference of sound waves that, first off, they're going to have the same exact characteristic. Okay, so you're going to have one sound generator over here, and you have another sound generator over here, and they're both resonating at the same exact frequency. Okay, so those two dots represent 2 speakers, let's say. Okay, so the 2 speakers, they're making 2 red circles, which are crests at once. They're making 2 purple circles, which are troughs at once simultaneously. And here's the animation of it going through. And as you're staring at this, you're probably wondering, do I need to copy this down? I think you just need to know the behavior of what's going on, and you'll be fine. All right, because drawing this, you can imagine how long it took for me to do it on computer. So drawing it by hand will probably take even longer. All right, at least on a computer, you can always Control-C and Control-V. Okay, so don't try drawing this out. Instead, just follow along with the narrative. You probably already know that the best seat in the theater is sitting at the dead center, right? And then here's the logical reason behind it. Okay, let's say that you're sitting right over here. As you sit over here, you're the same distance away from both speakers. In other words, with that person right over there, they're both listening to crests happening at once. So they're going to experience a super crest right over there. Okay, so you're going to hear a super crest there. Now, remember that it's an animation. It should keep on going. I just don't have the next part animated because in a few fractions of a second later, you're going to get a trough with another trough. So you're going to hear a crest and a super crest at once, and it'll get very loud. Then a trough and a trough both at once, so that it's the opposite phase. So your eardrum's pulled in the opposite way. Then it's going to be pulled in, out, in and out, and it's going to be very loud. Right. So the best spot, the best seats in the house in a theater is always going to be in the exact center. Okay. These are the best seats with all these red dots and purple dots. Again, it may seem purple at that moment, but remember, that's just a super trough. As time goes by, it's going to become a crest again. Okay. Would it hurt your eardrums? Yeah, if it matches the resonant frequency, and we'll talk about that later on. Okay. We'll talk about all the science afterwards. Right now, let's just talk about the behavior of waves, and we will have a lesson on how the ear generally works and why is it that when you hit 3 kilohertz, it gets annoyingly loud. We'll get there. Okay. Let's focus on this. Okay. So let's pull out another grade 10 term. Why not? You have a line over here, and you have another line over here. And you'll see the line in the middle is at the same distance away from the other two, and it's exactly 90 degrees to it. It's the perpendicular bisector. Remember that word? Now it's applied. All right. So if you're at the perpendicular bisector between two speakers, yes, those are the best points in the theater. But funny enough, if you sit right beside it, you're in the worst seats in the house, at least at that frequency. Okay. And this is what I'm going to talk about. Actually, I'm going to talk about all the other best seats in the house, and then I'll talk about the worst seats. Okay. So that's not the only best seat in the house. Another best seat can occur right over here that I'm circling, right? You can see that a crest is meeting up with another crest. You can see that a trough is making up with another trough, crest with a crest, trough with a trough, and you end up having this little curve over here, and this curve represents another good seat in the house. Same as right over here. That's another good seat in the house. Also true is right over here. So there are multiple good seats in the house, and I have it all animated out, so I'm just going to let the animation draw it through because it's always going to be better than my lines. Okay, so these are all the sweet and best seats in the house. Mind you that if you look at the wavelength in this diagram over here, it's of the same wavelength. In other words, the frequency in this example is constant. Okay, I haven't changed it. It's always the same frequency, whatever that number is. Okay, and those are all the best seats in the house. And yes, it is a mirror image on the other side as well. Okay, it's the same result. You'll see that in all these curves over here, I know I didn't draw it perfectly, but it's either you're sitting where a crest meets a crest or where a trough meets a trough. These are regions known as constructive interference. Okay, so the green lines are regions of constructive interference. These are the best seats in the house. But between the two best seats in the house, you're sitting at the worst seat in the house. You'll notice that directly between them, there will be a point in space where a crest meets up with a trough. And the reason why that happens is because of the spatial distance you are between the two. Okay, between one speaker and the next, you're just far away enough that because of that delay in time for the sound to reach your ear, it just made it to the next trough. Meanwhile, it's a crest on the other speaker. So a crest and a trough mathematically cancel out. And that will be the worst seat in the house. And I think I have those all dotted in purple. So beside all the best seats in the house are all the worst seats in the house. Often we pay attention to the worst seats in the house, and they're known as the nodal lines. All right, so these are nodal lines, and these are lines of constructive interference. Again, you only need to know the picture and understand what it is and what it means. So it's not necessary to copy it down. And these pictures are found in physics textbooks anyways. All right. Is it situational? Remember, I wrote down on the bottom when F is fixed. It is based upon that. Okay. It's based upon a particular frequency because the moment you change the frequency, this map changes. This map looks the way it does because we fixed the frequency. And I often do a demonstration in the classroom to prove to you that this does happen. So if you want to try it out at home, you'll see that I do have a file called demo A. And when you run demo A, this is what you need to do. It's not so good in a bedroom. You want to do it in a big space. So if your living room is huge, sure, do it there. If your basement's huge, do it there. If you got to do it in your backyard, that's probably the best place to do it. Okay. And you want to have two speakers that are built exactly the same. So hopefully it's, one left channel, one's the right channel. And you want to put it about 1 meter apart, because that's how I set up this demo over here. Okay, the demo works best when you have the speakers roughly 1 meter apart from each other. Demo A, if you look at it, it's nothing more than a very, very fun and exciting recording. It's everybody's favorite note, which is concert A. All right, it's a frequency fixed at 440 hertz, and it plays the same frequency on both speakers, both at once simultaneously. Okay, so if you have the chance to try to set this up at home, put the two speakers about 1 meter apart, outside is the best, and then start walking around. And as you walk around, you'll notice this, and it's pretty trippy. You'll stand in a spot where it gets rather loud, and you'll be smiling, saying, hey, it's nice and loud over here. I can hear that sound really well. But then you move, 1 foot to the left or 1 foot to the right, and then the sound cancels out. It just goes silent. Does it go perfectly silent? It won't go perfectly silent because you're probably doing this in your bedroom, or for me, I do it in the classroom, so the sound bounces off the wall. But the cool part is that when you're standing there, you don't hear the sound coming from the speakers anymore. You're just hearing the reflections off the ceiling and off the walls. So to you, it sounds silent, and you're just hearing this weird ambient surround sound. All right, so you stand to a point where it's like, wow, it's loud. I see the speakers there. It's loud here. You move over a bit. Whoa, it's gone completely quiet, at least from where I see the speakers. I'm just hearing the reflections. And if you do this in your backyard, it's even better, because it might become completely silent because the sound doesn't reflect off anything. It gets absorbed by the grass. And if you don't have any fences, it's even better. Okay, so you guys go and try that out at home for yourself. Okay. Now, remember, this only exists for this frequency. The moment I change the frequency, the wavelength changes, these waves separate even further apart, and the sweet spots will change. Okay, so there is no perfect sweet spot here, because it will always change. If you want something that's guaranteed to be the same no matter what frequency, stay at the perpendicular bisector. It's always going to be the best seat in the house. Everything else, it's going to be good or bad based upon the frequency. And that's one of the problems that we have actually with regards to some of the acoustics of a room, right? With the sound bouncing off the walls, if you're in a studio and you're doing an audio recording, there could be chances where the sound will mathematically cancel out, and you as a studio producer think that that sound is gone, or that bass sound is gone. So you accidentally crank it up, but then when you re-listen to that recording in a different room without those dimensions, you hear that sound really loud, and you realize that you've ruined your master track, right? So you have to go back and you have to fix it up and adjust it. Okay, and that's why when you're in a professional studio, they'll have these baffles on the side. They'll also have baffles in the ceiling and on the floor to minimize the reflection that can cause these nodal points to exist. Now you know. All right, it is a reality and something that you got to watch out for. Okay, but the whole purpose of the story over here is really just to tell you that you can have sound canceling out. That's the real big picture here. Okay, anytime you have a crest meeting up with a trough, you will mathematically cancel itself out. So please try this demo out on your own at home when you have the chance, and you can see that it does occur. Here's another demonstration that which does not work whatsoever through this medium here remotely. And that's because this recording is in mono. If it was recorded in stereo and you had speakers in front of you, you could do the demonstration with me right now and you'll see the outcome. And that's why I said I want to make a YouTube video on this when I have the chance, so that people can just try it at home and just see the amazement happen right in front of them. Okay, I'm not making this stuff up. This really happens. Okay, let's say that now with these two speakers, you can see that I've reversed the phase. In other words, I had a crest on one speaker and a trough on another speaker, and then there's animating out in real time. This time around, if you sit at the center, the sound will mathematically cancel itself out, right? You have a crest meeting up with a trough meeting up with a crest. It will happen when you're out of phase. So that's what I have next. I have this audio recording demo B. Again, if you have speakers at home, try this out. It's really trippy. Don't crank up and blast out the sound, because when you blast out the sound, you're causing the speaker's box to vibrate and other things in your room to vibrate, so it's not going to work well. Raise it up so it's just loud enough so you can hear it. Okay, so you can hear the annoying tone, which isn't much. It's like 10%, and you can hear it just fine. And let me just tell you what the recording is composed of. Okay. Now, when you look at it from afar, it looks exactly the same, but I did time out something interesting. You can see that there's these little hiccups over here, and the hiccups happen every 5 seconds. Okay, so let me just jump to the first 5-second mark. Where is it? Right over here. I can see the hiccup right here. Okay, at the 5-second mark, something happens. At the beginning of your recording, the two waves are in phase with each other. In other words, your left speaker, if it's a crest, your right speaker is also a crest, as you can see, right? Crest on the left, crest on the right. Trough on the left, trough on the right. And that happens for a full 5 seconds. And the moment you hit the 5-second mark, or the 5.03-second mark, because I was a bit off in my alignment, you'll see that I changed one of the speakers and I put it 180 degrees out of phase. In other words, instead of a crest, I make a trough, and instead of a trough, I make a crest. You can see that beyond the 5-second mark, now they are completely out of phase. Okay, this won't work so well on Google Meet, but that's because Google Meet, what it does is it does transform, edit, adjust sample rate, and it converts from a stereo recording and drops it down into a binaural recording. All right, so it's going to wreck everything that way. Okay, so it's not going to work so well that way. So that's why I've given you guys the recording so you can try this out yourself. Take 2 speakers, maybe even headphones can somewhat work if they're big enough. All right, and you'll want to place them beside each other. Or actually first put them out like this. Okay, so put them side by side. You play the recording, you hear the sound nice and loud in front of you. 5 seconds later, you'll hear that the sound seems to cancel out. They're not coming from the speakers, but it's the sound bouncing off the walls in your room, and you hear it as ambient sound. And that's part of the way how they cheat and make, virtual surround sound, by altering the frequency output as well as its phase, if they can get away with it as well. All right. So with you guys, what's really happening is that you have the speakers that are so close together, they're just touching each other, and this is the next demo you should try out. So first you do it like this, and next you'll put the speakers beside each other. Okay, so they're facing each other, kind of like one person shouting in another person's mouth at once. If they're shouting in phase, the noise that comes out in between becomes super loud because you get your super crests and your super troughs. But here's the trippy part. Let's say that a person on the other side changes their phase. As one person creates a crest, the other person sucks in that crest and makes a trough, effectively canceling it out. And then they reverse their behavior back and forth. Numerically speaking, they've canceled out their waves, right? The superposition of 2 waves, if they're out of phase, it will create a node. And here it is, artificially recorded for you so you can see the outcome, okay? In phase, in phase, in phase, in phase. At the 5-second mark, I hear the sound because I have stereo speakers here, but I'm sure for you guys at home, you hear nothing at all. Right. In phase, it's really loud. I gotta turn that off, sorry. Silence, I think. In phase, very loud, very loud, very loud. At the 25-second mark, it'll cancel out. Again, it's definitely going to happen for you guys because it's compressed the 2 waves and made it happen. It's just the consequence of this medium over here. I want you guys to try it yourself because it's a very trippy demonstration. Put the speakers side by side and you'll witness it happen. It gets loud for the first 5 seconds and it cancels out afterwards. It's pretty cool. Now, to explain what's going on here, I could show it to you because all we're doing is we're just transforming it. And how come it doesn't allow me to adjust the sample type? Oh, now, no, it doesn't. It used to let me do this. Oh, I need the raw recording because this is an MP3, won't let me do it. Okay, so what I would normally do is I would take this and I would just go off and transform it and switch it over to binaural. I'm sure there's another way I can do it by amplifying and mixing the channels. Yeah, I can't do it here because the program won't let me do this. But what I would normally do is I'd mix them together, and you'll see that the mixing will cause it to be loud at the beginning and cancel out for the next 5 seconds, loud, and then quiet afterwards. Okay? So it is a pretty trippy effect. You guys can try it out at home. Okay? And just to show you that this is a 3-dimensional problem, okay, because don't forget you have compressions, rarefactions, and this is happening in space, and you can't really see it on a piece of paper. So that's why it's always nice to have simulations so you can see what's really happening. Okay, I'm so glad about this guy over here. He ended up recreating all these really old animations. All right, these animations are pushing 20 years old, so they're not compatible with new computers. But they do a really good example of explaining what's going on. Okay, so we have these dots over here that represent a speaker. And I can lower down the simulation speed so you can see it happening at a slower rate. Okay, so they're constantly creating compressions and rarefactions, and once they interact with each other, you have this pawn ripple effect. Okay, where if you're standing where my mouse is, you'll see that it's either bright blue or dark black. In other words, you're hearing super crests and super troughs. So it's very loud right over here. Same as if you're sitting over here, it's going to be very loud as well. Same as if you are standing anywhere in this region here. However, if you're where these lines are, and that's why they're called nodal lines, these are regions where mathematically a crest and a trough meet up with each other, right? I clear this again, and you'll see that right over here, mathematically speaking, this is where crest and a trough, because of the delay in space and time, that they are out of alignment and they cancel out. Okay, and to answer another student's question about that, look at the nodal lines right now. This is based upon this particular frequency. If you change the frequency, the outcome will be different. As I lower the frequency, you'll see that these lines spread out. So the worst seat in the house isn't so bad anymore. The only seats that remain constant, no matter what frequency you're talking about, are the center seats. They always have the best sound profile. Okay, everywhere else, you may end up sitting in some dead zone. And that is dependent upon the frequency you're generating at. In general, with higher frequencies, you create more of these nodal lines, and at lower frequencies, you create less nodal lines. All right, pretty hypnotic. If you guys have a chance, try the simulation on your own. I'll link the simulation as well in the Google Classroom so you can try this out so you can see it. And I think the best thing about the simulation here, and this is my favorite part about it, is that this is a 2D profile here. It can also do this in 3D. Okay, and I love the 3D version of it because it really emphasizes what's going on. I'd like to slow down the simulation speed so you can see gradually these interference patterns happening. And here it is. So we're letting the Z dimension represent the amplitude. Okay, so if you're sitting where my mouse is right over here, you can see the ripples of the waves. It's a huge change in fluctuation between crests and troughs. That's why it's super loud over here. Meanwhile, if you have a boat sitting over here, you don't notice the disturbance because you're riding in a spot where the numbers cancel out. You're at a node. Okay, so this is a 3D version of a 2D version of a node, and now you know. Okay, why am I going through this exercise over here? It's to tell you that sound can cancel itself out. All right, so that's the ending of the first part of this lesson. The second part of this lesson is on a concept called a beat frequency. Okay, so when you have different frequencies interacting with each other, you end up having this artificial third frequency being generated. To answer that student question over there, you can check out a Veritasium video. Dr. Derek Mueller, he does the same exact thing. You go into a lake, and then you have these coat hangers, and at the edge of the coat hangers, you put a tennis ball there. Two of them with tennis balls, and you're like a super geek out there leaning over the pond, and you're just tapping it like this. And when you tap it like this, you're going to see the same exact pattern. All right. Dr. Derek Mueller on his YouTube channel, Veritasium, you can see it there. I think his was on diffraction grading. So you have to look for his diffraction grading video, and somewhere midway through, he's doing that exact thing that you're talking about. Okay, I hope that these recordings, I can monoralize it, if that's a word. I have a bad feeling it won't let me do it because I converted to MP3. Oh, this one lets me. Weird. I don't know why the other one wouldn't, okay? But what I have over here is a recording where the first frequency on the left, it's at 440 hertz. And the second recording down here, this is at 441 hertz. Again, normally I do this in the classroom, so you have two physical speakers. I want you guys to try this out at home as well. If you have two stereo speakers, bring them close together. They don't have to be big speakers. They can be the size of your fist. They'll work out just perfectly, okay? Place them far apart, see the outcome. Place them face to face, see the outcome, and you will see this trippy effect. You will create this third frequency, okay? So here's the first frequency at 440 hertz. That's left channel. The right channel will always be at 441 hertz. I will not modify it. Okay, so you can check in the audio recording. If you want to do a spectral analysis, you're more than welcome to activate the spectral analysis, and you will see I haven't changed the numbers. Okay, so it's first left channel at 440, right channel at 441, then the combination of the two. As I said, unfortunately, with regards to Google Meet, it's going to take the stereo recording and convert to mono, so you're going to hear the outcome immediately. But I want you to experience it in real life. Nevertheless, I'm going to play this right now, and this is the expected outcome. 440, 441. And there's the third frequency. It's very subtle. Do you guys hear that? Where it gets louder and quieter, louder and quieter. Again, it happens better with speakers than it does through Google Meet. Because with Google Meet, what it's literally going to do is that it's going to take the math of this two and it's going to do the most ideal environment. So it's not one of a room where you have echoes in the wall. It's one where you have an anechoic chamber. In other words, a room without any echo at all. And this exactly will happen in those ideal rooms. How come it won't let me do this anymore? Before it allowed me. Why not this time? Do I have to open the program again? because that's part of my lesson. I must have hit the wrong thing because now it lets me do it. Okay, so I'm going to convert this into mono, and I want, I don't know, 70% of the sound from each side so I don't blow out the speakers. So I'm going to take the stereo recording, I'm going to drop it down into mono. And that's probably what you heard, right? Okay, and that, my friends, is what is known as a beat frequency. It's the result when you have two different waves interacting with each other, you hear this third artificial frequency happening as well. And it really is just a relationship between the summation and differences of the two frequencies. If I switch this back into my old stereo recording, at the beginning of their interactions with each other, they are relatively in phase. Not perfect, but they are relatively there. Okay, let me just start rewinding back to the beginning of the two interacting with each other, and you'll see that they are roughly in phase with each other. Not perfect, but approximately there. But then at a different moment in time, because the other frequency is not the same as the first one, they will start to behave out of phase, like right over here. So they're slowly going in phase with each other, out of phase, in phase, out of phase, creating supercrests, supertroughs, nodes, then supercrests and supertroughs, then nodes as time goes by. And here's the thing that you might have noticed. I kind of gave away the formula there. All right, between 440 and 441 hertz, how frequently did this annoying thing happen? You probably witnessed it there. But just to confirm your hypothesis, here's another recording as well. This is example D at 440 versus 443 hertz. Okay. So the first recording on the left channel is at 440. The right channel is at 443. Then we combine them together and look at how often this annoying flutter occurs at that point. Again, on your side, because I know that you guys are hearing it in a monaural recording, I'll just edit that over here. Whoops. Hi. Oh, I have a visitor. Okay, little visitor. I'm in the middle of a lesson, and this is a live recording. Sorry, sunshine. Switch over to monaural. And again, this is probably what you're seeing right now, right? You'll notice that, yeah, these beats happen far more frequently. In fact, there's a time reference on the bottom right-hand side. So if I select one of these beats, you'll notice that this happens in 0.33 seconds. And if I still happen to choose 3 of them, that works out to 1 second. Okay? Let me just close this. I don't want to wreck the recording. And I think you guys have already hypothesized what the formula looks like. Between 440 and 441, you had a beat frequency of 1 hertz. Between 440 and 443, you had this annoying beat frequency of 3 hertz. And that's literally what the formula is. The beat frequency is the difference of those two frequencies. Now, as a listener, you have no idea which frequency is F1 and which frequency is F2, right? They're just two different tuning forks right in front of you. And you just arbitrarily call one 1 and the other one 2. In other words, a beat frequency cannot be negative. And to prevent it from becoming negative, that's why we have these vertical bars over here. And if you recall, these vertical bars, even though they're called absolute value, technically speaking, it's how far away the number is away from 0. And that's why it always gives you a positive answer. Okay? And that's what a beat frequency is. It's a difference between two disturbances. You end up creating this third frequency. All right, let's work through this mathematical problem right over here. A tuning fork with a frequency of 256 hertz is used to tune a piano. Okay. I think this is the only slide. So yeah, if it takes time for you to copy down that's okay, because I'm not changing slides after this. So if you want to, you can just follow along with the narrative and then copy down afterwards as necessary. And obviously this part over here, you don't need to copy down. That's just my hyperlink to open up the file. Okay, so a tuning fork has a frequency of 256 hertz. That's our reference tone. Okay, we'll call it F1. Okay, however, we had a second instrument, which is the piano, and when we play them both in unison, we end up hearing this annoying little flutter. So they aren't perfectly in tune with each other. Okay, so we heard what is it? The number of beats is equal to 9, and the time, sure, the time between those beats is 3.0 seconds. Again, the beat frequency is the number of beats over that time. You could also use delta t if you want to. All right, I'll just keep it as capital T. All right, so if 9 beats are heard in 3 seconds, then we're effectively hearing 3 beats per second. So our F beat frequency is at 3 hertz. So we're hearing this happening 3 times a second. Okay, and the question is, what is the frequency of the piano? And in truth, there are 2 possible answers. Okay, there isn't just one answer, there are 2 valid answers. So let's go through solving these problems properly. Okay, we are using the initial formula of F beat is equal to the absolute value of F2 minus F1. And there are 2 cases. That's why I'm going to write it out twice. Remember that the absolute value is one that's telling you that you must have a positive answer. It's the only way to conclusively get to a correct solution. All right. So if F2 so happens to be bigger than F1, then that's fine. This formula will work out beautifully as is, as F beat is equal to F2 minus F1 with the absolute values removed. So this is the first case scenario. Okay. We already have F1, so we're just solving for F2. So F2 is equal to F beat. And when we bring F1 over, it becomes positive F1. All right, so we hear a beat frequency of 3 hertz, and we're going to add it to our other reference frequency of 256 hertz. So one possibility that the piano can be tuned at is at 259 hertz. That is one valid possibility. Again, we're playing them both at once, so we really can't tell who's slightly higher and who's slightly lower. If you play them separately and you have a good ear, you could probably figure it out. But when they're played in unison, it's one of 2 possibilities, and you don't know which one is which. Okay, so there could be a case where F2 is less than F1. In other words, F1 is greater than F2. Now, if F1 is greater than F2, you're going to get a negative answer, and absolute value does not allow it. So how do we fix up the problem? Well, we just simply write out F beat is equal to negative of whatever you've done. And that will fix up the error. Okay, so if F1 is greater than F2, you need to put a minus sign outside so that the absolute value statement can still be true and valid. Okay, so expanding this out, we get F beat is equal to negative F2 plus F1. So if we want to find out what F2 is, when we bring it over to the left-hand side, it becomes positive. We get F1 minus F beat. So 256 hertz minus that annoying 3 hertz resounding gong in the background, we end up getting 253 hertz. These are the 2 possible frequencies that can exist when you have that beat frequency. All right, with that said, that's it for my lesson. Our point is the same exact story. So why not? I'll just leave that like this because it's the same story. Okay, I just wrote it out manually by hand. There's one more demonstration just to share with you, and this is the difference between, concert A versus concert A sharp, and then when I bring it 1 octave down below. You'll notice that this annoying flutter happens more frequently at the higher notes on the piano and is not as prominent in the lower notes. So if you have a piano at home, try that out. Between A and A sharp in the lower key register and A and A sharp on a higher register, you'll hear the fluttering happen far more frequently at the higher registers. All right, and it has to do with regards to the numbers that generate those frequencies. All right, I've already done the math for it. Concert A is at 440 and concert A sharp is at 466. If you look at the difference between those 2, that's 26 hertz. So you're going to hear this annoying 26 hertz background noise. Meanwhile, the lower frequency, you can see the differences are only 13 hertz. So it's going to be there, but it won't flutter as frequently. Okay, so demo E, I'll let you guys try it out at home for your own entertainment and a better appreciation of what beat frequency is. And I'll leave it with that. Why not? One more demonstration just to show you guys. Okay. I don't know how well it will come out as a recording, but some people like to tune their guitars using harmonics. And when they're tuning their guitars using harmonics, they are paying attention to the beat frequency. For example, if I want to artificially make my bass E 2 octaves higher, I need to make the string 4 times shorter. I can either press down on a fret to make it 4 times shorter, or I can naturally let it resonate 4 times faster by taking the string and forcing a node right over here, a quarter way down the string, which is coincidentally at the 5th fret, or maybe not a coincidence. Sorry. So this is the low E, and here's 1 E above middle E. And I know that this string up here has to be the same frequency. So if I play this and I play this, do you guys hear the beat frequency? I don't know how well the recording is, but I can hear it. I didn't tune this guitar perfectly because my daughter loves playing with it. She plays around with the knobs every now and then, and it kind of wrecks it up. In fact, if I detune it even more, you can probably hear that annoying flutter. So the objective of tuning guitar using harmonics is that you're going to keep on tuning it. Still there. Oops, tuned it too much. Still there, but it's much slower. Oh, that sounds beautiful, doesn't it? Okay, and there you have it. I've tuned those 2 notes so that they are resonating at the same exact frequency. That's how you do it using your human ears. Piano tuners, I know they're expensive. They're almost $200 to hire them to come in. They rely upon their ears, and they're listening for these beat frequencies when they're tuning the entire piano using just 1 tuning fork. For more fun adventures like this, make sure you like, click, subscribe, and make sure that you do your homework, because the homework fills in all the blanks. Catch you in the next